before you marked, the throughput estimate before you marked, and this is the throughput estimate after you marked. Okay? So basically, no, back. So basically, you're increasing delta, but the RTT will decrease. Okay? Now, it turns out that just by taking this formula next, you can actually have a closed form for the delta. So the maximum delta that will give you this property. Okay? So intuitively, what this happens is, if I'm ECN marking an MPTCP subflow, the effect may be that the subflow decreases its rate because it has options in other places. But if that MPTCP subflow is like a TCP connection, it has no other options, it will not decrease its rate. So this is the effect of this marking. Next. So we implemented this. Next. And this is how it behaves. So this is MPTCP. Vanilla over 11N. And this is the throughput you get. So you see that in this case, you're getting something like 30 megabits instead of close to 40. And on the right-hand side, something comparable, even less. And the red line is the one with ECN. So clearly, you get a lot better performance. Next. Just go next a few times. more. Okay. So this is the graph I wanted to show you. So this is actually this is a mobility trace. Okay. So walking from our office to the cafeteria, you're seeing a bunch of access points. This black line is TCP. That's well, it's actually multipath TCP, but connected to a single access point, detecting when the access point has died and doing a handover, right? So you get these periods of zero throughput just because it's so difficult to choose a proper threshold. Next. This is the MPTCP with ECN, so it actually works very well. All right, so this is the first use case I showed you. So what we did here is to use ECN marking to convince the sender to avoid the bad access points. I'm going to use the same mechanism in a completely different scenario now. Next. So this scenario is, let's say we have some ISPs that are greedy, none of them that we know, and they want to convince multipath TCP clients to move traffic away from the networks if there is a choice. Next. So the case we're looking at is this. We have, say, a mobile phone or a DSL client, doesn't matter, with two 10 megabit links. Okay. The question is, what happens if, for instance, ISPA decides to start marking or dropping the client's packets? Okay. Now, next. So the throughput MPTCP gets depends on two things. It depends on where the losses are coming from, right? So basically, when you have actual congested, one more. Yeah. So there are two cases. The case where the connection does not affect the loss rates of the link. So basically, you have such high statistical multiplexing that whatever the connection does, it doesn't really affect the losses so much. In this case, MPTCP will give you as per the goal we had in the design. So basically, you get the maximum of TCPA and TCPB. Okay. Next. The next case is when the MPTCP actually drive the loss rates, as in these links are not utilized by anyone, and only the MPTCP flow uses them. Next. In which case you get the sum of throughput. Okay. So if you don't do anything, right? If you don't mark in any way, MPTCP will get TCPA plus TCPB. Okay. Now, what the operator can do is to try to mark to move traffic away. Next. 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 Okay, so it's the same formula. Next. And here are the results. Okay. So on the first line, go next. On the first line, what I have is results when nobody's shaping. Okay. Provider A is carrying 10 megabits of this long-running MPTCP connection. Provider B is carrying also 10 megabits, and in total you get 20 megabits. Now, if provider A starts shaping as per that formula I showed you earlier, you get this line here. Next. Okay. So basically, as soon as provider A starts shaping, it manages to offload most of its traffic to provider B. And that's just because the MPTCP congestion controller reacts very quickly. It sees a higher loss rate, moves traffic away. Okay. So clearly there's an incentive for provider A to do this because all of a sudden now it's carrying a lot less traffic. Okay. If both of them shape, what's going to happen is that they basically each carry half of the throughput, and in total, MPTCP gets, well, 11 megabits, which is basically max of TCP-A and TCP-B, which is 10, right? So what happened is, when they both shaped, the MPTCP client went from like 20 to 10. Okay, this is a tragedy of. I have one more slide and I'm done. Just go next, a couple of times. One more. Okay, so this is what happens when you're running uncoupled congestion control. Okay, so when you're running uncoupled congestion control, basically the effect is more or less zero. Like, so nothing really happens. The effect in this case, if you look at the buffer sizes will actually be a lot less, so you get less buffer bloat, which is kind of nice. So the takeaway from this is I can program something that does this dropping without any per flow state. So I can basically have a table, and on every packet I can independently decide whether to drop it or not, without actually needing to know whether it's TCP or MPTCP. I can just turn it on for all the traffic, and it will affect MPTCP traffic a lot more than it will affect TCP traffic. Okay, and it's the same mechanism. And the takeaway of the talk is, you cannot just disable the coupled congestion controller. So the client gets a benefit from the coupled congestion controller in the Wi-Fi case, and in some other cases that I didn't have time to talk about. And the provider gets a benefit from the coupled congestion controller in this particular case. So everyone benefits from it. So it's not as simple as saying we'll just use uncoupled congestion control, because it's, yeah. So yeah, I'm done.
Okay, we are way over time, so I hope that, I mean, yeah, also because we started a little later because I had to wait for people to come in. But keep your comments and questions short, and I'd like the next speaker to come up and get ready also. But there should be any questions or anything. Like
nice talk.
Yeah.
Or really bad talk, right?
No. Okay.
So, hello everyone. My name is IETF93 from ISAE. Today I will present a new lower than best effort protocol named Flower with use fuzzy logic. Next. So I will start my presentation with a brief review of the two main LEDBAT problems. To keep my presentation concise, I do not describe here LEDBAT mechanism. For further details, please refer to the LEDBAT RFC. So you can see the left figures represent an example of a scenario in which LEDBAT show its aggressiveness towards a TCP neuronal flow. In this scenario, LEDBAT does not use enough to TCP neuronal and gradually takes over the link capacity. And on the right side is the latecomer unfairness problem of LEDBAT. In this problem, a latecomer LEDBAT flow can start ongoing LEDBAT flows. Next. So to sum up, LEDBAT does not have an optimal configuration and need to be tuned as a function of network condition. So LEDBAT is not adaptive. In fact, it uses a p-type controllers with two fixed parameters. So p-types is the p part of a PID controller. One possible solution now is to add an adaptive functionality inside of the p-type controller, but such scheme would require a good network model, usually too complex to derive. Next. So in our approach, we propose to replace the p-type controller of LEDBAT by a fuzzy controller. So our new protocol, Flower, aims at providing an LBE service while reacting better than LEDBAT front to congestion event. Next. Now the question is, why using fuzzy logic? So In fact, with a fuzzy controller, there is no computational complexity and no supplementary parameters compared to a p-type controller using bilet-bat. And the most important advantage of a fuzzy controller is that it allows us to incorporate our knowledge, our heuristic knowledge about how to control the system. In our case, how to control the queuing delay. For this reason, we propose flower as a potential replacement of bilet-bat. Next. So now, how do we control the queuing delay? As you can see on the figure, the red curve shows an example of the queuing delay, the evolution of queuing delay in time. So as bilet-bat, flower goal is to keep this queuing delay around a fixed target, as shown by the green light in the figure. To this end, flower fuzzy controller will take two inputs, the error or offset, and the chance of error or gradient of error. So the error is the difference between the target and the current queuing delay. It shows two things. The first one is whether the current queuing delay is below or above the target. And the second thing is how far the queuing delay is from the target. On the other hand, the chance of our error give us, show us how fast the current queuing delay is rising or reducing. So taking two inputs, the output of the fuzzy controllers is the chance of the congestion window, which is the value that we must add to or subtract from the current congestion window size. Now, the inputs and outputs are related by fuzzy rules. A fuzzy rule is generally represented by an if-then rule. For example, if we have a big negative error and the chance of error in this case is 0, meaning that we have an empty queue and the queuing delay is 0 and it is not rising now, so then we must increase the congestion windows as fast as possible. For further detail of fuzzy controllers, please refer to our article, soon to be available online. Next. Next. Now, I will show you the results of our new protocol. So the figure on the left is the running example from the beginning in which a bilet-bat flow can start a new Renault flow. And in the same scenario with the same network condition, on the right side, you can see that our protocol flower remains as an LBE protocol. I also want to point out that this is only a snapshot of our results. Using simulation, we test flower over a wide network condition, and the results show that our protocol flower behaves correctly as an LBE protocol on test case and even in the case where bilet-bat fails. Next. Now for the latecomer issue. So as you can see in the same scenario with the same network condition, flower can solve the latecomer issue. You can notice that at the beginning, flower used the slow start mechanism, but we stress that a slow start mechanism can have to mitigate the latecomer issue, but does not solve it completely. So, in fact, the slow start mechanism combined with the fuzzy controller can help us to solve the latecomer issue. Next. Now,
Yeah, Kulevin, very quick question. Did you also try lead-butt with slow start?
Yes, I try lead-butt with slow start, and as in many work, they try with slow start too. But I showed cases that why with slow start the latecomer issues still happen. Now, this is the most important part of this presentation: the interaction between an AQM and an LBE protocols. So, in the figure, the left y-axis represents the buffer plot intensity. That is the average Q length normalized over the buffer size. And on the right y-axis represent the TCP, the percentage of TCP throughput in the presence of an LBE protocol. So in this case, the ideal property of an LBE protocol is to minimize its the buffer plot intensity while minimizing its impact on a TCP, as shown by the gray shaded region in the figure. So now on the top of the figure, you can see the blue line and the red line. These are lead-butt and flower with dovetail queue. So in this scenario, you can see that both protocols behave correctly as an LBE protocol. But in the meantime, they also increase the buffer plot intensity. So using an AQM scheme such as RED can help us to mitigate, to decrease the buffer plot intensity. But unfortunately, in this scenario, lead-butt, as shown by the green lines, behave like TCP. Lead-butt is no more an LBE protocol. While our protocol, flower, shown by the violet curve, is more LBE compliant than lead-butt and tend to the ideal regions. Next, please. So, for the conclusion, the turning of lead-butt is very difficult and highly depend on the network condition. For the reason we propose flower as a potential replacement for lead-butt. We are currently implementing flower in the Linux kernel. Once again, I want to stress that flowers have low computational complexity, and there is a possibility for a more robust controller which be more LBE compliant using a narrow fuzzy controller. So I also want to suggest that novel LBE proposal should consider the impact of AQM. So for more detail about flower, please refer to our article soon to be available online. Thank you.
Dave Tapa from Blow.net. Thank you for citing that paper that we've done so many years ago. I am curious if you've moved on to trying out the new AQM, such as CODL, Pi, and FQ-CODL against your algorithm.
So I expect that flower would behave as with REST or with RED in case of CODL or Coden or Pi.
And with CODL and Pi, most likely, but FQ-CODL, it is unlikely. But I look forward to seeing patches, and I'll gladly try them as soon as you have them. Thank you.
Okay.
Was that it? Okay. No more questions, no more comments? Okay, I have one question. What are your next plans with this?
Sorry.
What are your next plans with this? What is the next happening? Are you going to?
I will now. My main concern is test flower in the real test bed So are implementing in the kernel in the Linux kernel now. So
maybe I can complete. So the next steps is to propose a draft to complete, I think, the RFC of LEDBAT, because we believe that today, if we strictly follow the linear controller proposed in LEDBAT, it fails. So we just want to propose an extension, but we have many tests, and we have to test inside with over RQM and in a real context, because at this stage we have a kernel implementation, but it's not stable yet. So we did all these experiments with NS2.
Okay. I think there is no single ICCRG meeting.
Emmanuel Lochin from ISAE.
I think there is no single ICCRG meeting where I don't mention that our list is way too silent. So please use a mailing list for this. Share results there and let people discuss it there. Okay. Thank you. Let's have the next speaker.
Sorry. Yeah, that one. Hello, so my name is Peter Szilágyi. I'm from Nokia Networks, and I'm going to present a joint work with Google. And, okay, next slide. Okay, so usual disclaimer, so this is work in progress and research, so I will make the necessary points on the way of the presentation, so we can go to the next slide. Okay, so what I'm going to talk is actually throughput guidance, a mechanism that we call throughput guidance, and what kind of improvements can be, what kind of optimizations can be made based on that. So actually, throughput guidance is about exposing network-side information to the data sources in order to enable TCP level or content level or application layer optimization mechanisms. And actually, the information that we expose is the available bandwidth on the radio interface. I will explain in what granularity, what that's the idea. And so actually, if you look in this picture, what I'm going to talk about is we have a throughput guidance entity located in the radio access network that actually is in the position to look into what is the network status at the radio. And then it exposes the information to the data sources. In that case, we did it with Google for YouTube servers. The exposure mechanism is already documented in a draft that I will show in the end. Okay, next slide. Okay, so this will be the agenda you will see. So we can go to the next one. Okay, so why do we need this at all? Very briefly, I think all of you know that TCP is not very good in making good guess in the beginning what will be the available bandwidth in the network. And that's why slow start was implemented at all. And later in the congestion avoidance stage, what it has to do is still to probe for the bandwidth in the network by increasing the rate and then experiencing loss and react to that. The second kind of problem is, okay, if the transport layer was very optimal in using all the bandwidth efficiently without creating congestion, but still using all the network resources, then still we have to harmonize the content layer with with the amount of resources that is there. So it's no use to start streaming down an HD video if you have just like half a megabit bandwidth. Okay, go to the next one, please. Okay, so how is the throughput guidance calculated? So how do we know at the network side what is available for a given flow, or what is the granularity of bandwidth allocation anyway? So some brief background. So I'm coming from Nokia, so we know exactly what we do actually in our base stations on the radio side. So actually, what is the standard in 3GPP networks is that each user equipment connects to the base station over a logical connection, which is called a bearer. And the resource allocation, the radio resource allocation, physical allocation is done per bearer level. So actually, we know what bandwidth could the radio allocate to each and every bearer. Therefore, we know exactly what is available in the radio. And then, very important thing, we also know if the radio is the bottleneck in the network or not. And it is very important to note that actually two things. First, there is no intention to signal a rate to a flow which is not there. So to signal a higher rate to a flow, which it couldn't achieve anyway if it went for the usual TCP mechanism. TG just helps it reach it immediately and sustain it efficiently. And the second note is that if the radio interface is not the bottleneck, so we actually have like losses in the upstream or something like that, we can detect that and we can react to that in the TG signaling. So either we do not expose anymore what is available, or we just signal that, okay, that's for you on the radio, but we know that you have bottleneck elsewhere, so you can adapt your data source accordingly. So actually what we have so far is we know what is the available bandwidth per bearer, and we know if we are allowed to say so. Okay, go to the next one, please. Okay, then I'm going to talk about how the data source can utilize this information. So first on the TCP level, what you can do is skip the slow start, skip this fluctuation during the congestion avoidance, just send at the rate which you are told. How you can do it? Adjust the congestion window based on the RTT and the data rate, because you effectively reach, thanks. Okay. So effectively get the data rate and you can stick to it. One note, you still have to obey the advertised window transmitted by the user. But pretty much that's it. One note, basically, packet pacing is a technique that you can use anyway without the TG to pace out the bursts that regular TCP connections usually inject into the network. But you normally do not know the pacing rate, so you just set it to a high value. But with the TG, you can stick to the pacing rate immediately. Go to the next one, please. Actually, these are results from LT lab test that we did with Google, showing what you can achieve, what is the gain you can achieve during the slow start phase of the TCP. So red line curve, regular TCP, you can see very nicely this exponential slow start. The green one, unfortunately, you can't see that well, but you have a green one which is just rockets from the beginning, and actually it delivers 3 times the throughput. Or you can download the same content 1/3 of the time. And the measurements with different RTTs are presenting pretty much the same gain. So please. Okay, but what about then when the slow start is over? Because slow start is over also when the slow start threshold is reached. This is how usual TCP, by the way, looks like. If it detects some loss, then it will cut back its congestion window multiplicatively. Actually, cubic is nowadays the most common one, so it will not reduce to 1/2, just like 75%. But if we knew that this loss, for example, was like a non-congestive loss, because some radio access technologies happen to have losses even if there's no congestion actually, but some errors, then we could instruct the sender, okay, just retransmit the packet, but do not drop the bandwidth. And go to the next one, please. That's what you can see here. So if there is some loss, which you know from the radio side that it is still the radio is a bottleneck and you don't have to react to this loss, then what you can do is just keep the pacing rate, which you can see like the slope of the data pacing is not changed, and then you can have actually, we can maximize the available bandwidth efficiently use it.
Do you want questions now, or would you rather save them till the end?
You can just say the question.
My name's Stuart Cheshire, and you need to stand in the box from Apple.
Yes.
The observation I'm making here is you're saying there are some radio technologies that have losses that aren't due to congestion, and the thought that occurs to me is when a packet is going 30 hops across the internet through to 2 different end systems far away, and there's a hop somewhere in the middle that has some peculiar properties, I would think that that hop is in the best position to know the peculiarities of that link rather than expecting something 30 hops away to compensate for it. And if it needs to be retransmitted there because you know it was lost, then just retransmit it rather than asking that guy over there to retransmit it through the network until it gets back to you sometime later. Just generate it locally.
Absolutely agree. If you have such mechanism there, for example, you have a Snoop proxy or you have something like that, then this is doable. If you have that, yeah, certainly.
Lars Eggert, so you must be aware that this has been proposed several times in the past. And going forward with your talk, maybe focus on what's different now.
Okay, let's just go forward and let's see. Okay. Okay, so far I was talking about TCP optimization, and then obviously you can use this information for optimizing the media itself. So you can channelize it into, for example, selecting the initial media rate. When you start YouTube video, then, okay, what rate to select. Nowadays, it is the choice of the client or some policy, but if you are told that you don't have that bandwidth, then it doesn't matter to start that. Google is currently not doing this, so it is more like a theoretical stuff. Okay, let's continue. Okay, some considerations which we actually received during the previous drafts that were focusing on how to expose actually the throughput guidance and not how to use it. So what if there are multiple flows within the data barrier, because actually then those flows interact with each other. What to do if there are both flows which react to the TG and do not react to the TG, or do not receive the TG at all. And what is if not the radio interface is the bottleneck? So let's go one by one. Next slide, please. So if there are multiple flows within the barrier, then actually we can calculate the fair share of each barrier and actually provide that for each, so the fair share of each flow from the barrier's bandwidth, and then send it, and that's it. Okay, let's go to the next one. If there are both guided and unguided flows, then you can argue that, okay, the guided flows can stick to a certain rate and somehow suppress the others, but you can do some kind of enforcement on the radio interface and separate the two kinds of flows, and make sure that actually the bandwidth is there, and the guided flows cannot send more than what you signal, so you can actually police what is happening there. Let's go to the next one. And okay, what happens if not the radio interface is the bottleneck? Then actually we can indicate that as well next to the TG, or we can just stop sending the TG, and then the protocol is that the data source is falling back to the usual TCP behavior. And maybe the most important is saved for the last, so let's go to the next slide. So actually we implemented this, and Google has implemented their part on the YouTube server side. And actually this is out there in a test network. And various quality of experience or application layer indicators were collected, like the time between you press the play button and actually the time it takes to start the video rolling. This is the join time, which is reduced having this mechanism. Number of formats used, this is improved a bit. Average video resolution as well. Client bandwidth improved a bit, but not that much. And the rebuffering time, so when you when the playing is paused and then the player rebuffers, this is also reduced. So actually, this proves that there are some benefits, not just like quality of service types of benefits that, okay, TCP is smooth and this kind of stuff, but okay, why do I care? Actually, I care because the experience of various applications improves. Maybe just one more slide that emphasizes the relations of two. So this is what existing drafts. It is not yet a draft, but it could be turned into a draft. But what we do have as drafts is actually how to convey this TG information from the client to the server. And the second is what are the high-level requirements. Okay, thank you very much.
You made a comment there, which I'll sum up as I tried it and it works, and that proves it would work if everybody was doing the same thing. And I think that proof requires more than I tried it and it worked, because one client can be greedy and show a 10% benefit. When every client is doing that, the internet collapses, so it's not a proof.
It's just a proof that in some cases it works, actually. That's all I could say. I
think we know that being greedy gets you more throughput. That's not a surprise. The question is whether everybody is greedy. What's the end result? That's the important
but actually,
question.
It's not that everybody is just getting greedy as everybody wants to get greedy. Actually, what we do know is what is the available bandwidth for each and every guy, and you can also enforce that the guy does not send more than what is there. But you can help the data source to reach what is there in the network efficiently. That's what it's about, actually. It doesn't have to probe why these usual mechanisms for the bandwidth it is told what is there. But you can police that. If you say this is 1 megabit and the guy says, okay, I have 1 megabit, let's say send that 2 megabits, you can scale it down.
When you set up the test environment so that your link is the bottleneck, then that works.
Yes, that's what I'm claiming.
But it breaks badly in cases, and what you need to do is to be able to know for sure that you are the bottleneck link. And if there were a way to do that, then TCP would be doing that already. So I think you can set up an experiment where it works. That's not the same thing as guaranteeing that it works in all possible scenarios.
Yeah, but we do not make that claim, but that's true.
So, Gary Fairhurst, you talked about the problem when guarded and unguarded traffic reach a bottleneck at the same time. And your solution seemed to be to separate the guarded traffic into a different service class. Is that right?
Actually, you can separate them to different buffers and do subscheduling, yeah.
Yeah, but you can do anything you like in your own network. You can run RSVP again, and you can control it completely. I mean, if this is an internet spec, then how are we going to do that in the general internet?
You can control them differently, but actually what the benefit, how it is realized, is that with usual scheduling on the radio interface, for example, even if you separate it into different service classes, you can't increase the rate of the source. You can just decrease it. You can buffer it, you can delay it, but you can't say that, okay, you can send even more.
No, my point was kind of like we're near the IETF here. We're kind of in rooms nearby. And if we're doing an IETF spec, we want it to work in the internet. Whereas what you seem to be talking about is use in a controlled environment. So is this just for use in a controlled environment where you control all the routers on the path?
Well, you can actually generalize this mechanism to put it into locations where there's a bottleneck. So we tried it actually in radio networks when the bottleneck was there. So like I said, it is the early phase.
Jana Iyengar, I think I want to echo something that Stuart mentioned earlier, that a proof of existence proof is not a scalability proof, right? I mean, we want something that's scalable, that's incrementally deployable, that doesn't do harm while it's being incrementally deployed. And those are considerations that are important, and those are questions that you will face again and again as the if this a mechanism like this, if you'd like to take this to the IETF. So one thing I would really value, because I've seen the presentation before as well, and I think that it'd be very useful to actually have answers to those questions about how do you do incremental deployability, and if those things collapse into existing mechanisms such as DSCP core points, or separating different traffic into different service classes and so on, then that's what the answer is. And that answer may not be enough. That answer may not be good, but that answer needs to be there in the presentation. Okay. There are a number of questions that this hasn't answered yet, and I'm happy to talk offline and discuss in more detail why there's a lot of work that has gone into routers signaling explicitly the rates that flows can have. This is not new, right? This idea has been there for at least, I don't know, 20 years, I think. I can point to work back in 2001 that actually talks about this, and there are folks in this room who actually worked on those ideas. And Michael wants me to leave the mic. So it'll be very useful to actually cite that work and to cite how this is different and why this is different and why those things aren't important, why those considerations in those works, in that work doesn't apply here.
Okay.
Yeah, Liza, what Jenna said, right? So ever since mobile network people came to the IETF, this has been proposed. I proposed it myself when I was at Nokia. So this is not new, right? And so there's a reason why we don't have it, and that's why I said if you in your presentation you could focus on what's changed, and I haven't seen what's changed. This presentation could have happened 15 years ago exactly like this. Well, it would have been 2G, but 3G, but
yeah, what it is.
So these are old designs that are being rehashed, and there are old arguments against them. And if something has changed, I'm totally open to revisiting this, but I don't think it has.
Okay.
So Gary Fairhurst, trying to be positive here. This is a problem we should try and solve, but we have to solve it in a new way. That's all I'm saying. So I like the presentation, but I think we need to see more.
Okay.
Different ways, perhaps even.
Matt Mathis, who as a longtime participant in the IETF, there are many cases where working groups have discarded work because it didn't make sense. And then later the net changed in some way that made it make sense. What is different is the advent of sort of two different things. One is various carriers, especially mobile carriers, are injecting all sorts of performance-enhancing proxies, for lack of a better term, that massage our TCP connections, which some of the content providers would rather not have in the path. I'm being polite. And the other thing that's happened is that a substantial fraction of the content is being delivered from CDNs and such fairly close to the edge of the network. And so in fact it is a controlled environment. And that there's a huge data volume that in fact only traverses essentially one ISP because it's cheaper for both the content provider and the ISP to deliver that data that way. And so there have been two changes that are unrelated to the technology that have made previously not useful, not scalable solutions have economic sense.
Okay.
Thank you for all the.
Yeah,
all
that's
not
a technical.
Oh yeah, no, you may come. But no more questions on this one. So I think I'll thank you and switch.
So hello everyone, my name is Emmanuel Lochin. I'm from ISA, Université Toulouse, and I'm going to present a work we did conjointly with the University of Delaware, and the objective is to add a non-relegable selective acknowledgement for TCP. Next. So as you might know, TCP is designed to tolerate reneging. So what does it mean? It means that the transport sender has to maintain copies of data in the send buffer until they are cumulatively hacked. So this design has been changed because there are several studies, and particularly a PhD thesis that demonstrate that it rarely occurs in practice. And even when it occurs, it does not really help the operating system to resume normal operation, in particular when the system is starving from memory. Next. So a quick recall about TCP/SAC. You might know all this stuff, but anyway, TCP send buffer gives a window of contiguous byte to transmit. The lower edge of the window is defined by the receive highest cumulative hacked number. The upper edge is defined by this number plus the number of bytes in the advertised receive window.
I think you have to hold the microphone a little bit away.
Sorry. Yeah. I speak a bit too loud. It's due to the beer show yesterday. Thank you for the advice. With this configuration, there is no advantage to having a receive window larger than the send window. Next. So to illustrate what I say, this is a normal TCP data transfer. And here we got the sender buffer. It got a number of 4 packets in its configuration. On the receiver buffer, we allow 7 packets. It's quite the same thing inside the GNU Linux, as the sender buffer is always smaller in the default configuration compared to the receiver buffer. And when we send packet, for instance, when we send packet 1, packet 2 is lost, and afterwards 3, 4 files arrived at destination are sacked, but even they are sacked, but the sender is obliged to keep all this packet up to receive a cumulative acknowledgement. It means here, the first observation we have is the size of the sender buffer is driving the size of the receiver buffer. Even if you have a highest receiver buffer, you cannot take benefit to use this size. So in green, it represents the packet that has been sacked, but cannot be freed from the sender memory up to the reception of a cumulative acknowledgement that will free all this packet. So you observe a decrease in terms of performance of the sender buffer. Next. While with the non-relegable option, you can have uncontiguous bytes of data inside the sender buffer.
Could you hold the microphone a little bit further away?
Sorry.
Because you are really loud.
Sorry. I wanted to be a singer, but...
Not here. Or sing.
Sorry, Lars. So I tried like that. Yeah. And so for the... in this case, you get uncontiguous number of bytes, data bytes inside the sender buffer, but you keep the receiver buffer busy. And you take advantage with this option of a larger sender receiver buffer. Next. So this is not a new mechanism, and it exists for STTP and MPTCP. Polymer has a draft for STTP and RSAC, and it does not only reduce the sender's memory requirement, but also improve the end-to-end performance. Yes? Okay. By the way, Quick implements an NRSAC-like mechanism. So the question we got was simply, does TCP still need NRSAC? And does suppressing, does allowing NRSAC inside the TCP connection would improve the end-to-end performance? Next. So the question, the answer are yes. No, I presume. Okay. The sender this improvement results when the sender buffer blockings occurs in TCP. Important thing, we never perform worse than standard SAC mechanism. We improve the end-to-end throughput, and following the default GNU Linux configuration, we can have an improvement as much as 15%. Next. So,
question, you measure with Linux, right?
Yes.
But Linux doesn't implement SAC reneging.
We have implemented the SAC reneging inside Linux kernel.
Sorry. How the specification of RC 2018 is not implemented in Linux. So if an RTO happens, yeah, you do not restart and retransmit all the data. Yeah. So if you speak about...
In fact, there's an errata about 2018 on exactly that issue because I wrote it.
Right. So my point is, if you make measurements, yeah, you cannot say that all improvements is about this because Linux doesn't implement the RFC. So it's...
in fact, we really observe that, and we you can trust me. At least I trust.
I trust you. That's not my point.
Yeah. But what you say, it's reneging is not implemented in the kernel. No.
Is that the underlying mechanism that the RFC that this bases upon isn't?
Yeah, there's one must in 2018, which the errata says should have been a should, and in particular that the receiver clears the scoreboard on a timeout.
Okay.
That there's an errata against that one word in 2018.
Okay. I miss it.
So I'm the first author in 2018. I'm Matt Mathis.
Yeah.
And the reason reneging is in 2018 the way it is to make the SAC robust in the presence of implementation bugs. And the problem is if you release the data and then it turns out the arithmetic was wrong on the SAC blocks, you're screwed because you can't fix it. You cannot do the right retransmits. I know of at least one case today that I don't believe that any middle box does correctly, which causes this condition. It doesn't happen very often, but it would be interesting to prove it. It'd be interesting to actually measure it in the wild. The situation is if I have a NAT that is rewriting a connection which has got symbolic IP addresses in it, ASCII IP addresses in it.
Yes.
Rewrites the IP addresses to change the length of the segments, and then loses one of those segments. The offset is different before and after the lost segment.
Yes.
It's not going to get those edges right. Mm-hmm. You're going to free the wrong data from the transmit queue. Yeah. The point of the language in 2018 was to make it robust.
Yeah, but
efficiency was not the goal.
Isn't it a feature if TCP breaks across such a box? That would be better, right? Because then the box will go away. No, my point, seriously, my point is that if we keep
if that was true, we wouldn't have them today because they break a lot of things. I've actually seen in the wild devices that were rewriting sequence numbers, a certain security appliance that randomized ISS by rewriting the sequence numbers and didn't fix SAC blocks. So the SAC blocks were out of window. I mean, there's a lot of really stupid things out there that just work because the senders were, we made the receivers have to assume that the senders could renege, so the receivers were robust if the SAC information was corrupted.
Okay.
And so the argument you need to make is not that it's more efficient, it's that the internet is robust enough without that fallback.
Okay. So one more question, if or maybe two more, but that's the okay. But the line is cut off the Gori.
Jana Iyengar, I just wanted to say that this is a brilliant example of designing the protocol to work around implementation bugs at the receiver, and in some cases, I mean, so as Matt was pointing out, it's possible that this has become more entrenched now. The bugs have become more entrenched now because this behavior is now expected at the sender. It would certainly be a worthwhile study to see if such bugs actually exist.
Gori, plus one, I was going to say, do the real experiment and tell us if there's a real problem. Because
over satellite connection, this is a real problem for us. And it really improves. We have over tests with satellite connection, and when you get very, very high delay.
Yeah, but listen to Matt's comment and get that right.
Okay.
Yeah, so the argument that is not needed, it has to be this, which is a very hard thing to prove.
Mm-hmm. Okay, I did cut the line off, so we really need to finish this and get to Gori.
And the discussion for doing an RSAC in SCTP was quite detailed and was for slightly different reasons because of the way the streams work. So you need to dig into that if you want to use SCTP as an example.
Okay.
Yeah.
Okay. Bob next, and thank you. It's good when it's lively. I just need to. And now we have that.
Hi, thank you. This is work on when Kuhn was doing experiments with very low Qs that you might have seen in AQM. We noticed there seemed to be something strange behavior, and so this talk, we haven't really done any more about this other than we identified what the problem was, and I did a bit of sizing of the problem, and it looks quite a large problem. It's a bug in TCP that I think is quite significant. When I say a bug, I mean it was actually designed to do this, but it's a wrong goal. So this is sort of the paper study we did after identifying what the problem was, but we haven't actually done any more, and we want to encourage other people to do something about this next. So I've very briefly explained here that a capacity-seeking algorithm like TCP, a greedy algorithm if you like, we now all understand, and some of us understood 20 years ago, we'll need an active queue management, right, to stop it just filling the buffers. And once you have those in place in deployment, and you've got your shorter queues, obviously you'll have shorter round trip times, because queues are part of the round trip time. And the congestion window that TCP works on is the packet rate times the round trip time. So if you make the round trip time smaller, the congestion window will be smaller. Yeah? Right? Now, therefore, AQM makes the congestion window smaller. And when we raised the number of flows to not unreasonable levels, I mean, we were getting, what was it? We had 40 meg and 15 flows, so that's 2 or 3 meg a flow, something like that, which is sort of how much broadband I've got at home for one flow. We noticed that as we increased the number of flows, the queuing delay started to grow, even though we had a really good AQM and we couldn't stop it. And this is because of the minimum window in TCP we discovered after working out what the hell was going on. Because in the code, when it divides by 2, if it's less than 2, it then rounds it back up to 2 MSS. And so, of course, this is to preserve TCP's ACK clock, but it means that TCP is fighting AQM. Because what will happen is, as the AQM keeps on signaling to it saying, close your window down more, shut your window down more, TCP says, okay, I'll divide it by 2 and then I'll round it back up to 2. I'll divide it by 2 and I'll round it back up to 2. So it doesn't ever get any smaller. And so we've seen this problem before. You know, this isn't new, but it's always been before that the packet rate was really low because of congestion. You know, the other side of the C-wind equation. It was always in congested environments, developing world environments, and all the rest of it. And Jana did a paper on this. I think he presented it here at one point, or your colleague Chen was the first author. And now we're starting to see, as we push down round trip times, we're getting the other side of this happening. And so it's sort of even important for people in the developed world, you know, so maybe something will get done about it. So next slide. So I did a little paper study on how prevalent this would be. So this chart has capacity on a log scale, log 2 scale on the horizontal, with some squares where different scenarios are relevant. I'll go through the whole thing. So you've got broadband in one square and data center in another. Broadband runs from 2 megabits per second up to 200 meg or so in this case. But actually the upstream of broadband is less than 2 megabits per second. And then on the vertical axis, the RTT, again on a log scale, in seconds from 1 second at the top down to a microsecond at the bottom. So that's why you've got broadband in the sort of, I don't know, 5 millisecond up to 100 millisecond or so, and data center in the hundreds of microseconds or tens of microseconds up to millisecond or so. And ignore the blue and purple stripes. That was just the template for getting shading required 4 stripes, not 2. I couldn't find one that only had 2. Not at speed anyway. So it's just the division between the red and green. And that shows you where you would have less than 1 congestion, a congestion window of less than 1 if you had 1500 byte packets and you had 10 flows, right? So equivalently, it shows you where you would have a congestion window less than 2 if you had 5 flows, right? And 5 flows isn't, you know, unreasonable. And you can see it sort of nearly cuts the broadband box in half and it slices the data center box off the bottom corner. Now, if we look at the text on the diagonal coming out the other side, you will get a congestion window below 2, even if you've got 1 flow in a data center that's got its MTU, so the TCP's MSS is 9,000 bytes, which is quite common in data centers. So if you have a larger packet size, that diagonal will push up further into the data center and may well cut it in half. So actually, about half the time, if we were using base round trip time, we will not be able to get any benefit from AQM because TCP will screw it up. Right? So we need to fix TCP. I would have liked to show another box for the developing world, but I hadn't had time to get good data on how many typical flows will share a link and where you might be. I don't know whether, are you coming up to say anything about that, or is that something else? No. Right.
Jana Iyengar, I was just coming up to say that this is, there's something very specific about TCP that's screwing up, and that is the inability of TCP to send outside of an ACK clock.
Yes. Well, I'm coming to that. Okay. I'm coming to that, yeah. And I think it's sort of strange we haven't noticed this before, but I suppose it takes some looking at to know what you're looking for. And also, we haven't had the experience of short enough queues, maybe, that this has been a problem before. Matt?
Well, there was a lot of work done at some point. I don't remember exactly the papers on a region that I refer to as exhaustion, where the fair share window size is less than 1.
Yeah. There's been a lot of work on the low rate side of it, but not the low round trip time side of it.
But it actually doesn't matter why you get into that region.
Okay, Bob, you really have to make a decision on whether in the remaining 4 minutes you're going to show all your slides, or whether you want to just discuss.
I think there's only 1 or 2 more slides.
3, 4.
Is that?
Something.
Okay.
Yeah.
Right, carry on. Next. What not to do is important. Can you go back? Yep. Don't use smaller packets, because you may, if you're getting something saying you're congested and you just use smaller packets, it may be packet congestion and you may make it worse. You don't know what the cause of this is. You don't know that it's low round trip time, high congestion, or what.
Aside from this point, and I totally agree with you on everything else you're saying, but current hardware can handle packets well down below 300 bytes because they have to. So you can cut the packet size by a significant amount from the MTU.
Right. No, you don't know whether you've got that hardware on your path. That's, yeah. Right.
Are you done?
No, there's more.
Certainly don't say, right, so the main point I want to get over is, those people that say TCP's got to be like this because you've got to have your ACK clock. The ACK clock is not a fundamental aspect of TCP. TCP is there to try and find a rate. And if you can't do that with an ACK clock, go and get a different clock. Like these guys did. That was the first. Oh, please, come on. I've still got one more point. I'm still within my time, and you're stopping me. So we need, and you can't fix this with the AQM, right? Because TCP just ignores it. Next. Right. So all I'm saying is we need a new pacing mode under a window of 2, and it needs to essentially do what TCP nice did, which is pace out the packets so that you get 1 over the window packets, round trip times per packet, rather than window packets per round trip time. Right? And I won't go with any of the rest. And the last point is just a summary of that TCP could well override everything we've been trying to do in the AQM working group. And it looks like IFC 5681 has to change, because it says you must break AQMs, essentially, if you paraphrase it. It says you must have this minimum, which means you must use an ACK clock and you must not use a better clock. Right? And so we need to change that. And a call for anyone who wants to work on this.
One comment, and then which?
Thank you for making me feel so special. Jana Iyengar. So I've actually spent a fair amount of time thinking about this particular space, and what you had on the last slide, which I wish was up there right now, is that being able to pace is not easy in general, but that's mainly for the large Windows space.
Yes.
But when you come down to the smaller windows, it actually becomes substantially better to get into the continuous time space. So when you're in larger windows, the key problem here is that the packets are discrete. And when you have large windows, the fact that packets are discrete units of data doesn't make much of a difference. It becomes continuous larger the windows become. When you come to small windows, the discretization becomes a problem. You can start reducing the packet size, but you then increase overhead and so on and so forth. It's a lot easier and a lot more sensible to move into the time domain and to stretch time, which is much more continuous.
One of the main problems with pacing at high speeds is that you're sending out a lot of packets before you get the next signal to tell you whether you were right. Because in this case, you're getting a signal within a round trip time, and you're sending the packet after that.
That's right.
And so you're a lot safer.
And yeah.
All right.
Yeah.
Thank you. Bye-bye. Sorry. It's like we're running over time. That's how it is. There's a break. We will have it. Sorry for that. Okay.
Hi, I'm Brian Trammell. I'm the guy between you and the cookies, so I'll try to make this quick. This is work done with Miriam Kulevind and Elio Gubser. Actually, Elio Gubser is the guy who did all the work. He's a master's student. He's awesome. On ECN Beyond the Web, we took some measurements from the BitTorrent DHT. So this is actually what ECN is. You should all know this. If not, you can go and get cookies now. Next. If you weren't here at the last ICCRG meeting when we talked about how we did this with the web, we basically probed the Alexa Top Million. We tried to connect with ECN. We tried to connect without ECN. We looked at the difference between the connections we got with ECN and without ECN. And we found that 99.5% of the time, ECN leads to no connectivity issue. About 65% will negotiate. These look a lot like the Apple numbers that we saw in TCPM a few minutes ago. So actually, there's a comment from Stuart, and he's like, yeah, this is actually pretty terrible work. Because what you're doing is you're looking at the web, which is the most challenging environment for doing ECNN, because you have all these nasty little front-end boxes in front of the web servers, and they're going to mess with your signaling. Go look at something else. So we decided, hey, let's go look at something else. Next slide. So we want a bunch of non-web servers. We want to try and connect to them. We want reasonably legitimate results. And then Richard Scheffenegger, I'm sure he's here, was like, okay, let's go. Oh, yeah, there we are. Let's go do a whole bunch of SMTP machines, because those are open, and they'll take a bunch of connections from place. And then nobody ever looks at high-rate traffic, opening connections to SMTP servers, trying one single command, and then shutting down. That doesn't look like spamming at all. If anybody has a need for some IPv4 space, I have some I can sell you for stupid cheap. So we looked at BitTorrent. BitTorrent has a distributed hash table that uses to point to content, and we had a meeting with our master student, and we're sort of telling him about this whole ECN thing, and we're like, yeah, okay, so we did, the Alexa Top Million. That comes down to about 700,000 unique IP addresses. This is a Friday meeting, and he's like, okay, well, how many do I need to look at? I'm like, if you can give me 10,000 addresses by Monday, I'll be thrilled. So he comes into the meeting on Monday morning, and he's like, well, I tried this thing out with a BitTorrent DHT, and I shut it down after 100,000 because I figured that was enough for this meeting. It's like, okay, cool, you're hired. You already passed. The rest of this is going to be bonus. The trick here is that you go to the DHT and you say, I want a torrent ID. And it'll point you to the next node, and it'll point you to the next node, and eventually you'll get to the node that has the torrent ID you're looking for. If you forge a torrent ID, if you just make up some random garbage, you'll walk the entire tree looking for it, and it's very, very fast, and you can harvest a whole bunch of IPv4 addresses for doing interesting measurement studies against. These are actual boxes that are connected to the internet that will actually take traffic that you throw at them. It's pretty cool. That's actually the fun part of this talk. The boring part of the talk is the actual results. Next slide. Yeah, this is really boring. The results are completely unsurprising. We've probed 687,089 IPv4 hosts. We're not going to report the number that we had of the ones that didn't have a problem, because lots of these actually did have transient failures, right? Between the time that we walked the DHT and actually went and sent the packet to go say, hey, do you speak ECN, something happened. We can report that we saw 0.21% where there was a definite problem connecting. So we tried to connect without ECN and with ECN caused a problem. This is lower than we saw with the web servers, but there's a bunch of noise here. No significant difference in connectivity risk between web servers and directly connected BitTorrent hosts, at least not that we can see with this study. 68% of Linux servers, or Linux hosts, and 1% of Windows hosts will negotiate. That's also not, given what we know by the defaults, not surprising at all. And the question that we asked last time, can we safely leverage client-side defaults to drive ECN deployment? And I guess you can actually ask the Apple guys how that's going for them. So, questions?
Dave Tott, bufferbloat.net. I love this method. The core problem that I've had with this previous experiment and the previous one is that it's not just ECN negotiation that's needed to test. Testing for what happens when CE is exerted in either direction would be best. And I'm curious what weekend you're going to do that on.
That's going to take 3 weekends. Okay. So we were actually able to get a little bit of data from the web server side of things. Those are all in the paper, in the PAM paper. That story is more depressing than this story. You see quite a bit of just weird signaling. Again, there are 4 bits. There are more than 16 ways to get the signaling wrong. The issue with the BitTorrent way of doing things is that you actually then need to, once you have the address, if you want it to keep talking to you, you need to know something about the torrents that are actually on that node.
Just get a random selection of movies and porn. You should be fine.
Okay, now I'm going to buy some dodgy IPv4 space for myself to go do that on. Yeah, so that's the next thing, and that's actually the second to next thing that we want him to go look at. We have some other stuff that he's working on right now, but yeah, that won't work nearly as quickly as this does. So that's not a weekend, that's not a quick thing. That's a kind of a long-running study. We're also looking at doing larger scale mesh measurements where we have sort of control of the content on both sides, and we really can get into this the depths of what can go wrong here. But that shameless plug for the Hops proposed RG on Friday morning. We'll be sharing an RG that hopefully we'll be looking into that in.
I have been modifying the transmission client for these things also, if you're interested.
That would be really cool. Thank you.
Okay.
Andrew McGregor. I have a suggestion for some unambiguously legal torrents to download.
That would be cool as well. So
Ubuntu is distributed as torrented ISOs.
Yeah, it is, but it's not on that many seeds.
Yeah.
And I found that doing that sort of thing terribly skews the results. You really do want to get what users typically get.
Right.
If you look for torrents, you find Linux users. If you look for the other stuff, you find Windows.
I think these are very nice final words, I think. So thank you all. And that concludes the session. Thanks.